Thanks so much indeed. You have nothing to say. Are there any questions? Um, Thanks for the kind invitation to this wonderful workshop on one of the most pressing and important research questions these days, which is, can we find, or whether in the first place, near-term quantum advantages for problems that have a bit of a utility feel to them in one way or the other. As you might have noticed, this is an excessively difficult question, sometimes unbearable, but I've tried to spend a lot of time with this question, so this will also be the topic of my talk. Of course it is. Yeah, 6 fingers. Okay, of course, quantum computing is not a new idea. Already in the 1980s, people like Feynman, Benjamin Deutsch were contemplating what kind of notions of computing would be conceivable if single quantum systems were the carriers of information, but only in the last 7 or 8 years, protagonists actually set out to build such devices to a reasonable scale, mostly driven by the US tech industry, but also by players in Germany, Europe, and in China. The machines we have are surely not yet fault-tolerant quantum computers. They're too noisy, they're too small, but then such machines as we have today with over 1,000 qubits were pretty much in the realm of science fiction not very long ago, creating an interesting state of affairs, and it brings the question on the desk whether we can reasonably hope realistic quantum devices of today or the near future to provide some sort of speed up over classical computers. There's reason for optimism in that we do know a couple of dozens of quantum algorithms that feature a super polynomial separation over classical algorithms, but there's still a bit of a mismatch, or at least one, in the sense that if you read the popular press, you get the impression that it's all about optimization, machine learning, and quantum chemistry. And if you're honest about it, these are not the type of problems we know as much as we would like to know about. And then it gets even worse when you want to think of near-term quantum advantages beyond random circuit sampling. Then it gets quite wishy-washy, and even my talk will be a bit like that, and there is a bit of a mismatch. So this talk, we will meditate on this. I will first come with the bad and the ugly, then some good parts, and then in the final part, the good, the bad, and the ugly. There will be a showdown, and we will see who survives, if anybody. Good. Obstructions. So the reason for being careful, cautious, and a bit depressive are the obstructions against quantum advantages in the near term, where I go into the lab and implement a quantum circuit. That was a joke. I mean, never let a theorist into the lab. Somebody else goes into somebody else's lab and implements a random circuit followed by measurements or estimating expectation values. Here it is. But if this person is doing that, this person is not quite doing it, but rather implementing a good approximation there, where there's the perfect circuit, say a bricklayer circuit of this kind, but this will be altered by noise channels that capture noise in decoherence, possibly modeled by on-site completely positive maps that sit there, which could be depolarizing. That's the plain vanilla, the Volkswagen of all the noise models, which just brings you to the maximally mixed state. But it could also be, say, amplitude damping or a non-unital channel of a kind. So this is what you have. N is the system size. You implement this, and of course you can implement deep circuits. There's nothing preventing you from that. It's a free country, but you're not quite implementing that, in the sense that even if you're implementing a deep circuit, all you ultimately have is a log depth quantum circuit. There have been interesting results on bringing you to the maximally mixed state in polylog depth or into the Gibbs sampleable ball for depolarizing noise, but even for general and possibly non-unital noise, it's true if you have a random circuit that on average you can just keep the last log n layer when you want to see what the impact is on Pauli expectation values, and the first part can be chopped off or replaced by the identity or by the birthday of your grandmother. The log the layers, log n layers, will eventually matter at the end of the day. So this is kind of an obstruction of a sort. This can be also made a classical simulation result, a dequantization result, in the sense that one can classically simulate on average, that's important, expectation values of observables to epsilon added position with probability 1 minus delta at any depth with this runtime, which means that if you're happy with constant errors, you can do this efficiently in any dimension. For 1 over poly errors, this would be efficient for bricklayer, nearest neighbor circuits in 1 dimension, and then the beautiful Zoltan light cone argument again comes into play in that this is quite related. But then if there's a classical algorithm for the same thing, then save the quantum resources and dequantize it, and please do it on your classical laptop. Can you undo the noise? Can you correct it? Sure, quantum error correction does that famously, but then we also know that quantum error correction comes along with heavy overheads of a sort. Can you undo the noise largely on the classical level? You can't. That's in the nature of quantum noise, that you cannot make it unhappen in a way. But there's techniques where you add noise, or where you do things, and where you largely kind of uncompute the noise on the largely classical level. It's not one method, but a portfolio of methods under the umbrella of quantum error mitigation, where you do stuff like adding different error levels at different like noise levels, and then you take data and then you extrapolate to zero noise to anticipate what the perfect circuit without noise would have done. It's a beautiful idea. It's called zero noise extrapolation. It's pretty much, or used to be, in the center of the IBM strategy. It's a good means to push the quantum volume to a bit more than what you have in the lab. Wonderful. It's also pretty cheap in that you don't need extra quantum resources to make it happen. So how far does this go? And that's a question we spend a lot of time with. Like, what is the limits to that? Like, is there ultimate limits against quantum error mitigation from the perspective of, well, information processing, if you want? And the abstraction we came up with is to think of this as a problem where you have noisy states given, sigma, and we ask a question of a sample complexity, in the sense that we ask how many copies of this noisy state is needed to estimate expectation values from a collection of observables to a given precision epsilon, and with probability 1 minus delta, in terms of the circuit depth, the circuit width n, and the depolarizing noise strength p, or some non-neutral channel analog thereof. So can you push it? And then we thought to bring this into the form of a hypothesis testing problem. You say, what? Why hypothesis testing problem? But if you think about this for a minute, you have a circuit given, and you put something in, say, a computational basis state or the identity, and then you want to do like a package of quantum and classical, but the least thing you want to be able to do is, when you send in a computational basis state or the identity, is that you want to find out what you have put in. If you can't do that, then you surely cannot do quantum error mitigation. It's a kind of relaxation of the problem. And then this becomes a multi-hypothesis testing. You can set up like a Fanos lemma with a right-hand side, and then this right-hand side has lots of two-linear entropies in it. And then the Zoltan and Jonas mindset comes in, where we thought, how can we make sure that these Renyi entropies become larger? There's these log-depth Clifford circuits that give approximate two designs that kind of match these two Renyi entropies on the right-hand side, and then you massage the right-hand side and get a bound of this thing that gives you a sample complexity bound of families, of large families of quantum error mitigation. So what we find is that one needs of the order e to the power of n times d many samples to achieve quantum error mitigation, at least in this abstraction. And previously thought it was e to the power of d, and since in the NISQ regime, d is of the order log n, our results are exponentially stronger than what was known before. Yeah, so this is somewhat kind of demoralizing, if you want. There's strong information-theoretic obstruction against error mitigation already at log depth, like n is like log of the system size, and there's the mathematician's joke that log is upper bounded by 4. It's a very good joke when you think about this. Plotted in MATLAB. So in other words, it does not say that quantum error mitigation doesn't work. We were cited like that, but that's not what we say. It can and should be done. It pushes the volume forward, but it does not scale in the most drastic of all senses, and it does not work well for all circuits. So the Jonas in the audience and so they think, wait a minute, the random Cliffords, these are like all-to-all coupled settings. So the locality comes in. This is a worst-case result. Maybe there's room for maneuver for more physically minded settings, feel inspired, but in worst case, this is what you have. Also, depolarizing noise, the Volkswagen is catastrophic. Oops, I haven't said this. Oh, is this recorded? Anyway, and I did, that's right. Like non-user noise is special in some ways, in that not on average, but for certainly highly structured settings, it can be even good because you have a sink of entropy, and there's this kind of cute quantum refrigeration scheme that's a bit like quantum error correction. On average, there's nothing you can do, and log depth is all you have. So the glass is half empty or half full, depending on how you put it. No need for depression. Logarithmic depth is all we have, but then it's all about numbers, right? It's citing David here, he is. It's not all about asymptotics, but numbers matter. The average gate fidelities, oh, this is missing. It's like of the order 0.999 for 2-qubit gates as an average gate fidelity, and that gives you pretty deep circuits if you look at the numbers. And quantum error mitigation can increase the circuit volume. Near-term quantum advantages are challenged by only having log depth. It's challenged by obstruction against quantum error mitigation, but numbers matter at the end of the day. It also invites to think more in terms of intermediate steps, say coherent versions or new types of coherent versions of quantum error mitigation, or even think of steps between error mitigation and fault tolerance, because error mitigation is not a been there, done that effect. This is presumably there to stay even in the near-term fault-tolerant setting, or even the fault-tolerant setting as a primitive. It will not scale, but then it's not all about numbers. I'm always citing Ian Wormsley for him being an experimentalist, and as experimentalists are not asymptotic people. Last Wednesday, I gave a talk in Bad Honnef about this, and then I was not citing Ian Wormsley because he was in the audience. It was over, and then Ian said, "Oh, I'm an experimentalist. We're not asymptotic people." Lesson: think about the numbers and not only in asymptotic terms. Is there hope for useful near-term algorithms? And in all honesty, I don't know. And this part of the talk will be not so much of a scientific talk, but a core dump of things I know on that question, hoping that it will contribute to the greater good of this conference in one way or the other, because it's a difficult question. Say, are there constant depth quantum advantages with a practical feel to them, not in the sense that they settle your financial portfolio problem necessarily, but that do something beyond just random circuit sampling, so that you can argue that if you sample classically up to a constant error in the total variation distance, that you would get the collapse of the polynomial hierarchy, but some problem that has a bit of a more practical utility feel to it. That's that dream. And here's a candidate in the sense that there is a PAC learning advantage for constant depth quantum advantages. And to remind you what this PAC setting is about, that's the probably approximately correct setting where you have a family of probability distributions, a generator that spits out samples, and the task of the learner is to stare at these samples and learn what's going on. So the learner takes samples, thinks about them, and it's trying to spit out new samples from that distribution, or slightly more pedantically put, for every epsilon delta given access to the sample oracle, the classical data oracle, outputs in time poly in all the parameters with a probability at least 1 minus delta, so probably a generator of a distribution that is approximately correct. Again, you take pictures of cats and dogs, you meditate, and you generate new pictures of approximately cats and approximately dogs with high probability. That is generator learning, that's PAC generator learning. It's a nice mathematical framework, and in this sense, there is a PAC learning advantage for these shallow circuits, where the idea is to construct concept classes from quantum advantage from shallow circuits. These are sampling advantages of an unconditional kind that built on beautiful work by Bene, Watts, and Parham, which in turn builds on beautiful work by our invitee, who happens to be out in this moment, which is kind of put into the form of a hyperplane learning problem to make it a proper concept class that you want to learn. And there's a separation of concept depth quantum over log depth classical circuits under meaningful locality constraints. This is not a quantum machine learning problem that's solving the world, but it's a mathematically meaningful learning problem where there's a separation shown of quantum, constant depth quantum over slightly larger classical beyond just sampling. So I think it's a baby step, but a healthy baby step in a good direction of seeing what we can do along these lines. Are there simple learning algorithms? So what? Didn't the guy just speak about learning algorithms? Yes, but there's kind of two types of learning. The quantum machine learning, and then what was used to be called quantum systems identification. Like you take data in the lab and you want to do property testing, tomography, and so on. You take data and you want to learn a property of the system. Is there a near-term reading of that? Yes? And here it is. In a setting that aims at identifying the symmetry properties of a quantum state, that's the state sister or brother of the famous hidden subgroup problem that we all know and cherish, in the sense that if G is a finite group with a unitary representation and H is a subgroup of G, then you have access to copies of a state, and this state is promised to have the property that it's symmetric under the subgroup, but if you're not in the subgroup, then you're at least 1 minus epsilon away in the sense as is written here, and the problem is to identify the subgroup H. And that problem rose to prominence with the beautiful QRP plenary talk given by Adam Boland, who also looked at a cute application, namely the hidden cuts problem, where you have a pure state and you have cuts, and the aim is to identify the cuts as a specific reading of this state hidden subgroup problem, where we revisited the question and thought hard about this and understood that you can kind of formulate this in terms of like a certain P of M, a character P of M that incorporates the symmetry properties in the right way. And then all you do is you sample from the output distribution of these P over M's, and from that you can efficiently estimate H, the subgroup in the state. It's the same algorithm, but it's much simpler and has a much reduced circuit complexity. And in this formulation, it's also easier to come up with applications that are more, in a way, physicsy. We looked at qubit and qubit stabilizer groups. Then global symmetries of quantum states, also in the sense of symmetry productive topological order that was just mentioned a minute ago, where you find of the subgroup in a cluster state, say. Then cuts along the state is entangled. Well, that's the same thing, but then also like hidden translation symmetries. There's a couple of new applications that we put out, and in work to come, we also look at the robustness properties thereof, which are interesting because it's quite robust. It's a relatively near-term quantum algorithm of doing something relatively meaningful and relatively practical. I think that's a fair way of putting it. So my meta message here is think of quantum learning problem when you want to see where there might be something to be done for near-term quantum algorithms. So this is not so much of a science talk, but more like an advice lesson. Here, this question that we had just in the previous talk, can mid-circuit measurements help? And mid-circuit measurements are interesting, friends. Well, you have the circuit, you do a measurement, and, well, that's not a new thing. I mean, measurements are very old. But this has risen into prominence a lot in the condensed matter or condensed matter inspired community. People have been thinking about preparation of quantum states. I mean, this was even mentioned or implicitly mentioned in the question to the previous talk, whether, say, you can prepare GZ states with constant depth circuit. No, you can't. There's a topological obstruction in a way, if you want, if you write this in terms of MPS, if that's your preferred language. But with mid-circuit measurements and auxiliary systems, you can do it. And people have been thinking of what to prepare with mid-circuit measurements, and that's great, but then you can ask, and that's basically your question that I pick up, whether one can use this as an algorithmic primitive and help in near-term quantum algorithms of the type that we have in mind here. And the answer is, if you want to get something done, mid-circuit measurements do help. And that's, again, not very practical, but it's what is probably the case, is that sampling from a constant depth one-dimensional IQP circuit, just to remind you, an IQP circuit is a family of borderline classical circuits where it's hard to sample from classically with the usual like fine print, and that sampling up to a constant error in the total variation distance is hard in the sense that you would get a collapse of the polynomial hierarchy to the third level. But this is possible to constant depth, and you could compress it if mid-circuit measurements are around. And this is cute. That's not a result in its own right, but it motivates you to think in these terms because it tells you that this is a powerful computational primitive to use these mid-circuit measurements to do things that are provably impossible otherwise. Not so much in the circuit preparation realm, that was your point, but in the algorithmic primitive sense. That's my invitation. We also follow up on this on geometry-informed IQP sampling frameworks for learning ground states. This seems to be similar to what you said in your throwaway remark in the questioning hour. We should talk about this, of using Fermi sampling and so on. Here we use this for like a measurement-driven variational ansatz, which actually vastly improves over standard variational methods. It's kind of a cute intersection of using sampling as an algorithmic primitive rather than doing unitary variational circuits. Can we improve quantum algorithmic primitives like the Hadamard test? It's another advice. Yes, you can. In the sense that usually in the Hadamard test, there's one register that you use and the other register that you don't use. But then, because there's no information in it, but there is. And we revisited this, and we looked at this noisy garbage state and used classical shadows to extract as much information as we could from this garbage. And it feels a bit dirty to look for stuff in the garbage, but using classical shadows, you can get something out of this, and you can improve the Hadamard test using that. So here my advice is that it's good to combine near-term quantum algorithms with ideas like classical shadows to squeeze as much as you can out of it to hope to improve these algorithmic primitives of a kind. Can quantum algorithms change meaningful definitions? This is not so much of a near-term algorithm, but can new insights of quantum algorithms challenge what we think is a meaningful definition in quantum information in the first place? And this is something that we came up with not so long ago, which surprised me massively, in that there's 30 years of quantum computing theory and 30 years of work on entanglement theory. I did my PhD on entanglement theory, and these communities don't talk so much with each other somehow. At some point, we looked at just at the notion of the entanglement entropy as the von Neumann entropy of a pure state that captures entanglement in pure quantum states. And it turns out that the operations you need to do to still entanglement or to form it are not efficient. But then what point is there in quantum communication if the resources you're using are not efficient? If you look at efficient state manipulation, it's all different. Like the min entropy features are no longer the phenomenon entropy. I find that interesting. This is like more quantum algorithms in your head, but it's still cute that after all this time, you can challenge the results of Charlie Bennett and others in a way. So the phenomenon entropy, entanglement entropy makes use of inefficient transformations. Which brings me also to my last point of this part. That's good because I have more time for questions and a bit of joint meditation. I guess it's fair to say that the realm of quantum computing that is closest to utility is that of quantum simulation. I mean, of course, it's great to think of learning tasks, optimization, and so on. There's good evidence that quantum simulation is the place to be in. And of course, we know that, say, time evolution of local Hamiltonians is BQP complete. So in a way, it's like a quantum computer. But that is a true statement, but it misses the point that the typical instances we have in typical quantum simulators they're not the hard instances of that problem. And it has become a kind of common theme to raise quantum simulators against state-of-the-art classical simulators and kind of benchmark them against each other, and also see like which part is stronger, and in a way that's also nice because both parts get stronger over time because also classical simulation methods are improved over time. I mean, I think we started this race in 2012 and we kind of raised a MPS simulator, that stands for many paper state, against a cold atomic quantum simulator that's efficient for short times and you can kind of run the algorithm, but for long times the time and entropy is too large. And that was run on the fastest computer the German taxpayer could afford. At a time in Germany it was still a major economy. And like with 5 weeks of runtime per plot, which is like an upper bound for an algorithm if a PhD student is involved, using the fastest algorithm at the time. And then you see that for short times you get good agreement, but for long times you have to stop, but then you can ask better questions on the quantum simulation than on the classical one. It's not a quantum advantage in a way, right? One has to be careful, but it's kind of good to see that this race of quantum over classical simulation is a healthy thing. There has been nice work by the kicked Ising model or by IBM and also recently by D-Wave. Yeah, it's kind of interesting to see that a day later Staudemeyer had a classical algorithm doing the same, but I'm not so negative about this in the sense that both fields do grow with this and there's no schadenfreude involved. I think it's a good thing when we do this. But it also shows how difficult it is to find sweet spots of quantum over classical simulations. For ground states, classical tensor networks are just very strong. It's unlikely to be a good candidate for a quantum simulation beyond classical means. Presumably, we have to go into 2 dimensions and also non-equilibrium to reach the sweet spot of a quantum simulator beyond classical. But it also emphasizes, and this is my meta lesson again here, that we should think of new methods of benchmarking. Say of Hamiltonian or Liouvillean learning, where, say, you take data at different snapshots in time, which is efficient in space and inefficient in time, which you can do up to a certain time, and then you use ideas of like super resolution or manifold optimization to learn the Hamiltonian up to a certain time, and then you can make predictions on the quantum simulator, but with more predictive power because you've learned what your Hamiltonian or your Liouvillean is in the system. This is what we did for and with Google. We calibrated the Sycamore chip with them or for them, which is cute in its own right, don't get me going. But such techniques can increase predictive power. We should think in the near term about benchmarking techniques that augment the results that we have to get utility for near-term quantum algorithms. Which brings me to the coda of my talk. So, near-term quantum advantages are not easy, surely. Constant factors matter. We should think about numbers. I think David's talk that I apologize, I missed, was about numbers. This is very important, that it's not only about asymptotics, but numbers matter. Quantum error mitigation can grow the volume a bit, and we should do it. We have not shot it down. We said it's not scalable, but asymptotics is not all in life. But that's only part of the issue. The other part is we need robust advantages, not just knowing something about highly structured points of a kind, but we want to have families of instances where we can say something meaningful about. And that's not so easy. So we've done result on optimization where we found that you can approximate, say, hard instances of integer programming well on a quantum computer that are provably hard to approximate on a classical computer. That's motivating. Google has followed up on with decoded quantum interferometry, with wonderful work that relates approximate solution of certain optimization problems to certain families of decoding problems. It's a very fresh mindset and a very healthy setting. I have a question to the audience, but for reasons of time, I will maybe ask that later, because we have a nice QSAT algorithm that has a gap in the problem. I ask you about this because I would like to get your advice. But the point I'm trying to make is we don't want cute points where we can say, we've proven a quantum advantage, but it would be good to have like a robust advantage of a kind. And that proves to be very difficult indeed. Like one candidate that I'm aware of that we came up with that's of this kind is in the machine learning context where we looked at quantum versions of probability diffusion models where there's a forward process, a sampling setting, and a backward process where we could show a separation of quantum learners over classical ones under certain structural assumptions on the data, which we could check for industrial style data to see whether they're satisfied. But that's nice because that's at least a setting where there's hope to find an advantage for families of circuits instances and not just for individual points. I'm just saying this, that having a proven point somewhere will not be the end of the story, but we want robust near-term quantum advantages to make progress here. But anyway, I think it's an exciting moment. It's a good research question. I'm very optimistic about this. I think when I give public talks, I often end them by saying that quantum computing is interesting, even if you restrict yourself to saying things that are true. I think that's a good guideline. I think as long as we stay away from the hype and take it step by step from the near term to the long term regime, I think we should be fine and this should be interesting. Any time within the next days or so, together with John and Steve, we are putting out like a perspectives article where we go from the near term to the fault-tolerant regime, where we kind of identify like pockets of stuff to do along the way. Well, this will make it presumably for Friday. Let's see how it goes. So to end, I've asked in this talk whether we can reasonably hope realistic quantum devices to provide a speed up over classical computers. And my core message of this talk is it's definitely maybe. And on this note, I thank you very much for your attention. I'm looking forward to questions you might possibly have.
Okay, do we have some questions for Jens?
Maybe I can start with my question.
Sure.
Can I? You see, in this optimization business, people are struggling. It's not so easy to find advantages. But one thing that's sometimes overlooked are polynomial advantages in optimization, which are still exponential either way, but quantum to classical. And what we do have is for this Simon-Benjamin algorithm of a measurement-driven SAT solver, we found a polynomial advantage over classical algorithms with a proven guarantee, only that the theorem has the gap of the Hamiltonian in it. That's awkward, right? Because how would you estimate I mean, of course you can use Knabe bounds for certain frustration-free models, but the interesting things are all-to-all coupled. Do you have an idea of when it's meaningful to have a quantum advantage, a polynomial quantum advantage in an optimization setting where the gap is part of the theorem? Yeah.
So in that setting, okay, so in that setting, what you have is that you do a lot of rounds, right?
Yeah.
And then it's an exponential many rounds, but classically it would be also exponential.
Yes, right.
But with bigger exponents.
Yes, that's right.
Yeah. But then, I mean, if you would have such a result and you don't know how big the gap is, you can always hope that it's small and then run it, right?
Right, that's what I write in the Outlook. It's like a
Yeah.
bootstrapping technique. Yes, I
Yeah.
mean, it's great. It's a theorem. It tells you what's going on, but you can just run it and then morally invert it, say when it functions, there's presumably a gap.
Yeah, yeah.
Okay, fair enough. Yeah.
So in this race of simulations, like physical simulations versus computer simulations that you said, started in 2011 or 2012. So how far can the simulators, the classical ones, go today? Right now, I don't know, 13 years later, is still the entropy building up a limiting factor, or are there better algorithms now that can basically follow this 1D spin chain forever?
Oh, that's a wonderful question. Okay, a couple of answers to this, if I may. I keep it short. Even at that time, people tried like fitting methods. Of course, you can fit simple curves to it, and that's of course with few parameters you can match the curve. But that's missing a couple of points. For example, it's not about retrodiction, but prediction. It's not about one plot, but about a family of plots. You want to learn the functional dependence of your control parameters, of your setting, and the family of plots that you get. So fitting is not the answer, so to say. But that wasn't your question either, to be fair. I would think that nowadays you can pretty much go to the end of this through a couple of algorithmic improvements. Yeah, so things have not been stationary, so these tensor network techniques have been improved a lot. And there's also other techniques that are just limited in completely different ways. For example, if you have an interacting fermionic model with quartic terms, there are settings where you can take this thing and then do like Wegner type flows of this guy to a diagonal Hamiltonian. And when it's diagonal, then of course you can look at time evolution for arbitrary times because it's diagonal, it's a trivial time evolution. Now you make a mistake from going from the interacting part to the diagonal one. But you can see along this trajectory, you can make a bound to the error. That's kind of interesting way of a limitation because you're not limited in time, but you're limited in accuracy. But you have a guarantee for it. And that's another type of challenge of these quantum simulators because you can say I can do it for all times, but with an error bar that grows. Yeah. So you had a short question. My short answer is yes, you can do it now, but that wasn't my point because I also said that both sides grow, and it's true that also the classical simulation methods become a lot more powerful. And when Stoudemire does it again, he also makes use of more powerful algorithm. In fact, we are doing quite a lot of tensor network simulation for circuits, and sometimes it goes for idiotically large circuits that you can't believe, which you think you get a bit worried about what you can do classically. I mean, I do. Thanks for the question.
Okay, so maybe let's take the rest of the discussions to the coffee break.
Thanks.
Thanks, Jens, again.